This computer. 됐다. 웹사이트래. 그 프레젠테이션 공유는 어떻게 해드리면 될까요? 이거, 인턴 폴더에 있는 게, 아니, 어떻게 들어가 계시니? 오케이. 잠깐만. Okay, so I'll get started with my lab meeting presentation. So for the past 2 months, I've been working on the SVC occlusion device project, and specifically on the sensors part. So today I'll be sharing with you the general project overview, the device actuation flow that I designed, the 3-band sensors that I've tested, and the barometric sensor that I have designed. And I will conclude with some of the discussion questions that I didn't have time to answer before I leave. So what is our device doing? Our device is trying to address heart failure. And for those of you that are not familiar with what heart failure is, your normal heart looks like figure one, but for some reason, your heart's ability to pump out blood gets disrupted. The heart has to adjust to it, and your heart turns into something like figure two. And when your heart becomes like figure two, you're like in a very big danger of heart failure. So there's many ways to mitigate this, including the precardia therapy as illustrated in figure three. Precardia therapy is where you insert a catheter, which is a very thin tube that you insert through your SVC. SVC is superior vena cava. In Korean, it's called daedongmaek. And this catheter has a balloon attached to it. And this balloon will get inflated and block off the SVC to temporarily limit the blood going into the heart. And because the volume inside the heart is reduced, it is expected for the pressure inside the heart to reduce as well, providing temporary relief to the heart. So what is our project doing? Our project consisted of two parts. First is the animal testing, where we're verifying that the external occlusion, by pinching the superior vena cava from the external, can yield the same result as internal occlusion by doing it with a balloon. Second, we are developing an occlusion device that will occlude the SVC from the exterior to a desirable percentage. So this is the actuation workflow, but that's a lot of text. So I'm going to replace it with some images. The blocks that were covered in the image is illustrated by the red circle that is highlighted, and it's essentially just the actuation feedback where a sensor value is used to ensure that the device remains in the actuation state that it's in. And if you look at the 3 blocks on the bottom right, this is the condition required to activate occlusion of the device. First, it's going to check how much time elapsed since the last occlusion. And if enough time elapsed, it's going to check if the central venous pressure, which is the pressure inside your superior vena cava, is higher than the set threshold. And if this high pressure was maintained for a long time, it is going to activate occlusion, reduce the blood going into the heart, providing temporary relief, and expecting the heart condition to actually improve. So the 3 sensors that I've tested, the first sensor is strain gauge, and strain gauge has a characteristic of changing resistance when strain is applied. But since the change in resistance in strain gauge is very small, it has to be connected to a Wheatstone bridge setup and also connected to a low cell amplifier. And the HX711 low cell amplifier that I used has a 24 bits ADC resolution. And the setup that I used is illustrated in figure two, where 2 strain gauge sensors are attached on the front and the rear end of the device to detect the strain of the device. And I also took a lot of effort balancing the bridge with resistors with small tolerance errors. And also I tried to minimize the wire length and solder all the components so that I could remove any unintended resistance caused by wires. The second sensor that I tested is a Velostat sensor. And Velostat is a special material that has a characteristic of decreasing resistance when deformed or when stress is applied. And the basic structure of the Velostat sensor is simple. You would have the Velostat in the middle and 2 electrodes placed on both ends so that you can think of the Velostat as essentially a potentiometer. But instead of you turning the knob, it's going to change resistance when it's bent. So I have tried many different fabrication methods to make the sensors, including simply sticking the electrodes with a velostat with a Kapton tape, applying conducting grease between the electrode and the velostat to ensure that they're connected, casting the sensor in silicon, applying adhesive and applying pressure so that they remain in contact, and finally applying conducting proxy. And I'll show you later that all these methods miserably failed, so I just threw away this idea in general. So the last sensor that I tested is a flex sensor that was sold by Spectra Symbol. And this flex sensor has a characteristic of increasing resistance when it's bent. And the specific working principle behind this is that it has conducting particles, and when the sensor is bent, the distance between the conducting particles increase, thus resulting in increased resistance. So the commercially available sensor has many characteristics that doesn't fit to our application. So I went through some of the processes to remove the undesirable characteristics, which first starts with removing the stiff plastic layer from the back of the sensor and cutting the sensor to a desirable shape, making a hole using a needle in each of the circuits. So you can see the top thin line is the first part of the circuit, and the second alternating color line is the second part of the circuit. And after making a hole through each of the circuits, we will put a wire through it and make a hook-like shape so that the wire doesn't escape. Put a masking tape to ensure that the two circuits are separated, and finally apply conducting proxy so that the wire can connect to the circuit. And lastly, to get the data from the sensor, I would connect it to a Wheatstone bridge, Potter bridge setup. So in order to test the feasibility of three of these sensors, I tested with a fixed deflection test, where I created a very simple setup of turning the screw on top of a first gray plate. And as the screw is turned, it will push down the other transparent plate beneath, and the sensor that is attached to this transparent plate gets deformed. And I wanted to test if the data from the sensor is consistent and reliable. So the result of the fixed deflection test, I will start with the strain gauge. But before I get started, this graph has a lot of lines, and this format of graph is going to continue for the rest of my presentation. So I'm going to explain to you this graph at first. So I'm not sure if you can see, but there's the green line, which is indicating that the motion that's supposed to replicate expansion starts. The orange line is supposed to indicate that the expansion finished, and the blue line shows that the occlusion started, and the purple line shows that the occlusion ended. And the yellow horizontal line is supposed to show a steady state data when the sensor is in expanded state, and the sky blue line is supposed to show a fixed value when the sensor is in occluded state. So for the strain gauge, I could see that there's distinguishable consistent states. However, there were large overshoot and undershoot observed, and there were a lot of fluctuation and noise present in the data, as you can see from the wiggly lines. And this is the infamous velostat sensor. I tried so many things, they all failed. So let me go through with you one by one. The first design that I tested is the Kapton tape version. You can see in this data, I can see distinguishable and consistent states. However, there are large undershoot observed, and also there's a lot of fluctuations and noise as observed by the wiggly lines, along, just like the strain gauge. The second design was when I tried using conducting proxy to ensure that the electrode and the velostat remains connected. There is kind of a distinguishable state, but you can see that the way the data moves is quite unexpected. I expected all the bend sensors to behave like the graph one, but my sensor said no. He wanted to behave like that. I still don't know why it looks like that. So if you think you know why, you can let me know, because I really don't know. And the third version is the silicon casted version of the sensor. And first of all, this graph is a mess. This doesn't have any distinguishable states, and there's high fluctuations as observed by this two big red question mark. And just to let you know, in this state, nothing happened. Like the sensor was staying still, nothing happened, but then the data just fluctuated. And at the end, I decided to leave the sensor as it is to see how the data is going to behave. It just decides to like increase to like some weird value without any apparent reason. So I don't know how to explain that graph either. And because I didn't know, I decided to just not use velostat. The last sensor that I tested is the flex sensor. And this sensor has become my savior. Like, this is the best graph that I was able to obtain from all the testings. First, we can see a distinguishable and consistent states, and there's no significant undershoot or overshoot observed, and there's minimal fluctuations or noise present in the data. However, there is some stabilization time delay, meaning that the data actually takes a little while to get to the steady state value. But this was observed in all the other sensors, and as compared with other sensors, Flex sensor showed the most reliability. Therefore, I decided to use Flex sensor as my sensor to place on my device. So to integrate the sensor to my device, uh, I'm from presentation last week or 2 weeks ago, Jonghyun explained to you how the device operates. So I'm not going to go into the details on how the device actually works. Instead, I'm going to focus on how the Flex sensor was integrated into the device. So in this first design, I installed the Flex sensor on the occlusion SMA layer throughout the entire length of the device. And this is the graph observed from the data collection run, where alternating states between occlusion and expansion was made to see if the value remains stable. And we can see that the initial data when no motion was done, and the data after the device came back from expansion to occlusion shows a little difference. But other than that, there's distinguishable consistent states. And one problem with this design was that the flex sensor with the stiff layer of plastic was used in this design. And therefore, this hindered the expansion motion of the device. And the device also had a tendency to occlude back when expanded. So this was something that we wanted to improve in the next design. While we were developing the next design, we also tried testing the strain gauge on the device. And the reason why the strain gauge was slightly offset from the center of the device was because we were worried that if we put it in the center, the deformation in the center would cause too much deflection in the strain gauge, resulting in break. And apparently, this choice was a very bad idea because this data is also another mess. First of all, it has a very indistinguishable and inconsistent states. And also, it's also showing unexpected patterns. And what I've realized from this graph is that when you place any bending sensors in silicon, there's a tendency for your sensor to behave or like react only when there is active deflection. And when the deflection finished, it has a tendency to like go back to its original value. So whenever you're going to use any type of bend sensors in the future, maybe it's not advisable for you to cast it in silicon. And this is the second iteration of device placement. So as I discussed before, the stiff layer of flex sensor actually hindered the expansion motion. So we thought that if we put it only halfway, it's going to not disturb the motion. It didn't, but the data was also bad. So first of all, the sensor was very insensitive to state change. You can see on the y-axis of this graph that the value is very small. And there was distinguishable but inconsistent values in each state, meaning that this sensor placement was not ideal for actuation feedback. So at this point, I made a transition from the Arduino to DAQ. And this was a recommendation from Chiop. He's not here today. I wanted to thank him. He's not here. But using DAQ allowed me to make many improvements, including greater data collection resolution and sampling rate, minimal output fluctuations, and low common ground voltage fluctuations. And also there were greater data processing expandability because DAQ uses MATLAB to code. So this is the third iteration of flex sensor placement. This time, the flex sensor was installed on the same location as the first version, but then the stiff layer was removed. And this actually allowed, well, first of all, the flex sensor was close to the occlusion SMA, so there were some temperature effects from the SMA. And we also observed that this sensor placement has only significant deformations in the center. And so the entire sensor length is not actually utilized in keeping track of the device actuation state. And finally, even after removing the stiff layer of the flex sensor, there was still hindrance to expansion. But then we will also observe that this sensor placement helped with the occlusion motion. So this is the last iteration that we did. Instead of putting the flex sensor on the occlusion wire, we decided to place it on the expansion wire. And this design has many advantages. First, it's not the sensor wasn't casted in silicon. The version 3 was also casted in silicon, but this time the sensor is left exposed outside. And there's less temperature effect from SMA because there's some distance between the sensor and the SMA. And we believe that this design more accurately reflects device actuation status because the two ends of the sensor is connected to where the expansion wires are connected. And as the device occludes, the sensor would actually come together, and this would result in more significant change in resistance of the sensor. And we also observed that in contrary to the version 3, this sensor placement hindered occlusion and helped with expansion. And this is the same kind of testing that I did as compared to the first version. And we can see that there's distinguishable consistent states in this design as well. And this is a plot of how the sensor value behaves at different percentage of occlusion, assuming that there's superior vena cava installed between the sensor. And we can see that there's some kind of like surge polynomial pattern. And I'm assuming is because the device has a tendency to, as it gets closer to its final expanded or occluded form, it has a tendency to kind of like actuate more. This is kind of hard to explain. So like there's a tendency for the sensor to like bend more. So I'm assuming that's the reason why. And by using the sensor, I was able to achieve percentage occlusion control of the device. But these two videos are 4 minutes in total, so I'm not going to play it. Instead, I have images of sensor the devices being in different percentage occlusion. The first, this is the left video is the version 2. No, sorry, version 3. Version 3. And you can see some significant changes by your eyes, but the version 4 is it's kind of hard to like distinguish each state. And this is because there were some problems with the occlusion motion of the device. So we're developing a new version right now, which we didn't finish yet, but we're expecting it to show significant differences as it is. But there is some differences, and I was also able to check that the sensor is able to keep the device's shape as intended. Okay, I'll move on to the second sensor that I have tested, which is the barometric sensor. And with reference to the EVAC paper that our professor wrote, the EVAC paper used barometric sensor that was casted in silicon to sense intravascular pressure. And we thought that we could do the same thing just with superior vena cava by buying the same sensor that they used and casting it with a snap-fit casted barometric sensor to install an SBC along with a pressure ring. So this pressure ring is going to clip on to the superior vena cava, and we expected it to measure the intravascular pressure. So before we moved on to actually using it in superior vena cava, we tried to see if the data is consistent with fixed mass test. And this data also showed a lot of problems. So first of all, there's inconsistent data at same mass after heavy mass is loaded. So after 100 grams, and when you load back the 50 grams, there's a big difference between the 50 grams before and after. And there's inaccurate response to change in mass, because you would expect the difference between 20 grams and 50 grams to be smaller than the difference between 50 grams and 100 grams. That wasn't the case. And we're still investigating why this is happening. We are assuming that this could be because we casted the entire sensor in silicon instead of only casting the barometric part, but we're still looking into it. And lastly, the data showed a tendency of increasing baseline value slightly as we load more masses. So these are some of the problems that we experienced. We also tried installing the pressure ring to the SBC Phantom that was developed by Tomin. And we can see a very similar pattern here. And let me give you a quick explanation on what these voltages mean. These voltages actually indicate it's proportional to the pressure inside the SBC Phantom. So we would expect the data from 5.5 volts on the left and right to be the same, but you can see there's some offset here and there. So here are some of the discussions that I have not yet answered. And unfortunately, I would not be able to answer because I'm leaving on Saturday. First is if there's any alternative or better FLX sensor placement so that we can minimize hindrance to actuation and better represent actuation status of device. Second is resolving inconsistent data obtained from barometric sensor and finding out why that is happening. Third is replacing relay, because I'm currently using relay to connect the SMA wire to power supply with other switching components so that SMA can be excited and turned off more faster. And lastly, minimizing thermal effects on bend sensor from SMA heating, which also relates back to the first point. And that's it for my presentation. Oh, this is a quick video that I found. You should watch it. It's funny. Oh, there's no sound. Yeah, so this is basically my 2 months of experience. I thought I found the solution by finding flex sensor. Apparently not. Our research is just a wrecked car. Anyways, thank you for your attention today, and I would entertain any questions if you have any. Thank you. 네. 하나 샘플이 어떤 말씀이시죠? 아, 네. 그 버전마다 하나씩 만들었습니다. 네. 네. 아. 음. 아. 네. 네, 저도 사실 그거에 대해서 좀 걱정이 많았는데 이제 정현님이 말씀하시기로는 이제 디바이스 디자인은 거의 다 완성이 돼서 앞으로 나오는 거는 이터레이션이 비슷비슷할 거다라고 했는데 이게 아무래도 손으로 만드는 거다 보니까 이제 플럭츄에이션도 있고 센서 자체도 지금 이 센서도 사실 플렉스 센서가 커머셜리 어베일러블긴 하겠지만 베이스 레지스턴스가 제품마다 좀 조금씩 달라가지고 분명히 플럭츄에이션이 있을 거라고 생각을 합니다. 근데 이제 저희 목표는 제대로 하나만 만들자. 여기이기 때문에. 그리고 이게 그 아까 보여드렸던 이 그래프는 이거 말씀하시는 거 맞죠? 이거는 사실 제가 오늘 데이터 컬렉션을 한 거거든요. 그래서 컨시스턴트한지는 다양한 디바이스를 아직 테스트를 못 했는데 그것도 지금 굉장히 고려할 사항인 것 같습니다. 아, 이거요? 네, 이게 사실 플렉스 센서가 지금 이 버전 4면은 항상 구부러져 있잖아요. 항상 구부러져 있으면 데이터가 이렇게 왔다 갔다 거립니다. 그래서 이 데이터가 왔다 갔다 거리면은 이 데이터를 써서 릴레이를 껐다 켰다 해야 되는데 이렇게 플러큐에이션이 심하면은 릴레이도 엄청 껐다 켰다 할 거잖아요. 그래서 저는 이 데이터의 무빙 에버리지를 써서 데이터를 그 액추에이션을 하거든요. 그래서 이 지금 너무 얇아서 잘 안 보이는데 이 빨간색 줄이 이제 무빙 에버리지거든요. 그래서 여기 이걸 써서 저는 지금 액추에이션을 하고 있습니다. 이렇게 플럭추에이션이 있어가지고 질문 없으신가요? 그럼 여기까지 하겠습니다. 감사합니다. 네네. 못 봤습니다. 어, 디바이스 자체를 측정해서 어, 사실 오늘 시간이 너무 많이 남을까 봐 이 슬라이드를 안 했는데 이게 아까 방금 보신 이 그래프를 측정한 방식이거든요. 터졌다. 잠시만요. 이게 어떻게 하는 거냐면 일단 아까 질문하신 거는 이제 플렉스 센서를 달아서 디바이스 액추에이션 단계. 그러니까 이제 디바이스가 얼마나 좁혀졌고 얼마나 벌어졌는지 그거를 매저를 하는 거고 이제 그 수식을 써서 이렇게 리짓 SDC 모델을 만들었는데 이게 왼쪽 위에서부터 100% 그리고 오른쪽 아래가 이제 10%거든요. 그래서 이거를 껴서 각 센서가 어떻게 나오는지를 보고 그 센서 관리를 토대로 만약에 우리가 SBC를 한 70%로 업그레이드 하고 싶다. 그러면 이 밸류를 코드에 넣어서 그대로 이렇게 그 모양을 잡게 하려고 하고 있습니다. 네, 네네, 맞습니다. 네, SMA의 저항이요? 어, 음, 네, 맞습니다. 근데 제가 사실 그 SMA는 잘 몰라서 혹시 SMA가 이게 모양이 바뀌면 레지스턴스가 바뀌나요? 그럼 혹시 그 레지스턴스는 어떻게 그걸로 디포메이션 어떻게 해야 될지 제가 이해를 못하겠어서 아, 아 진짜요? 저희는 그걸 모르고 저희 그냥 이제 FMA 무지성 솔트 소켓 하고 야 전기 흐른다 야 뜨거워진다 이렇게 하고 있었기 때문에 근데 사실 그것도 이제 좋은 방식인 게 이거는 일단 결정적으로는 디렉트하게 매저하는 건 아니잖아요. 서페스에 붙어 있으니까 사실 그렇게 해서 릴레이션십이 잘 나온다면 좋겠지만 지금 저희 디바이스가 큰 문제 중에 하나가 익스펜션 SMA랑 오클루션 SMA가 열 교환을 좀 하면서 서로 이펙트가 있거든요. 그래서 그거를 좀 그 디자인을 하면은 이거를 좀 생각을 고려를 좀 더 해야 될 것 같습니다. 근데 정현님한테 추천은 드려보겠습니다. 이 아이디어. 쓰시면은 여기까지 하겠습니다. 감사합니다.